Hey, good morning, class. Hope everybody is fine. So today we're going to be continuing our conversation on the force of friction. Alright, so from last class, as you recall, we finished on the following. We talked about that friction is a force that arises at the contact or interface of two materials moving against each other. That the force of friction is a vector always against the motion and is proportional to the normal force times the friction coefficient. The reason for friction is that the surfaces are usually not smooth, right? So they don't glide against each other, and actually all the roughness actually gets and holds and scratches against each other. So this is the reason of the friction in general. However, I did mention that for very smooth objects they can actually stick to each other because now we have the van der Waals forces acting. This is something we will discuss in a different time, but just remember the name. One of the ways to reduce the friction is to fill this gap with something like a lubricant, right? So that definitely reduces the friction. So this is, for example, why the car tires will skid on a wet surface, and then you have to be careful when braking during the rain. And then we'll look very briefly at the inclined plane, where we saw that the normal force is not just the force of gravity, right? It's the reaction force of the support. And for a flat surface, it's just the full mg for the object, but on the inclined plane, this was the mg cosine of the angle, right? And it's directed in the opposite direction than the corresponding projection here of the gravity of the object, of the mass on the inclined plane, right? So, but the friction force is going to be directed opposite to the motion, if this is the direction of my motion, and again it's going to be the friction coefficient times the normal force. Today, I want to add to it that there are two types of friction coefficients, or types of friction, and one is called static, and second one is called kinetic. Many of you tried and figured out probably from your experience, if you have a box with some mass standing on the floor and you need to push it, it's usually hard to start it moving, but once you start it moving, it continues to move faster or easier, so it's easier to keep it moving. And this is because, as a rule, the static friction coefficient is larger than the kinetic one. In some particular cases, it could be a much bigger difference. For example, if we consider a skater on ice, right? So we have the smooth surface of the skate blade standing on a smooth ice. If you're just standing there, imagine that there is a wind, so let's draw schematically. A person standing here, there is a weak wind blowing, so if you're stationary, it's not enough to move you around. But once you start moving, that wind will be able to sustain your motion. The reason for that is that between the blade, the edge of the blade, and the ice, something will change, right? So in a static case, you have this blade and ice pushed against each other, and whatever roughness is on the surface, or the van der Waals forces in our case, actually are holding them together, making them stick, so it's hard to move one against the other. But as the blade starts moving, the physics changes, because the high pressure of the blade on ice will actually melt a very thin layer of ice and make it into water, so the interface will be lubricated. Therefore, the friction coefficient will drop dramatically. But this is a special example that shows that a very big jump is possible between the static and the kinetic friction. In normal life, the difference usually is not that drastic. I mean, here the static can easily be probably 0.8 or 0.7, and the kinetic is going to drop to about 0.1 or less, right? So this is one of the biggest kind of natural occurring drops differences between the static and kinetic friction that I can think of in the simple example. In normal examples, like with the box, the static would be probably 0.8, and the kinetic, I would estimate it to be about 0.6. Alright, so any questions at this point? Let's quickly recap. We have friction. Friction is the friction coefficient times the normal force, which is the reaction force of the support. It keeps us from falling through support that we have. There are two types. There is a static and a kinetic friction. Static coefficient is usually larger than the kinetic one. And you can think of it as the change in physics on the interface. And whatever are the interfaces and whatever is the change in physics, it doesn't really matter in each particular case as long as you know those interfaces. The table in your textbook actually lists both. You're welcome to go and see that the friction of two materials, say rubber on pavement, is actually different if the tire is moving or not. And so there are many examples. Alright, if there are no questions, I'll continue with the example. Alright, so the simple problem, let's take this particular example. We have a box standing on the floor. A student is pushing it with certain force. And now the question is the following. First, what force is needed to just start the box moving? And the second question, what will be the acceleration of the box after the box will start moving? So for the first question, we'll look at the box, we'll draw a free body diagram. Right, so we have gravity acting down on our mass. Right, so it will be mg with the negative because it's directed downwards. The normal force will be equal to it exactly, so it's going to be with the opposite sign, just mg. And therefore, when I apply my force, F, the friction is going to be opposing to the force, and it's going to be static coefficient times the normal force. So in our case, friction is 0.8 times, well, let's designate mass to be 5 kilograms. Alright, so it's going to be times 5 times 10. Again, we're taking G10 for the simplicity of the calculations. Alright, so that will be 40 newtons. And it's directed in a negative x direction. Right, so I can call it a negative 40 newtons. In order to overcome it, just to make it move, my force must equal by its value, by modulus, right, by absolute value to the friction, so that will be just positive 40 newtons. Right? So this is how you would solve the first part. Now, what happens as the box starts moving, my friction coefficient changes. So my new friction, and I'll call it like kinetic, it will be now a different friction coefficient, right? 0.6 multiplied by, again, mg times 5 times 10. So this is going to be 30 newtons. Right? Again, it's going in the opposite direction, don't forget the minus. And now we will see that, well, you see mg and the normal force and gravity, they balance each other. Therefore, we can discard them, right? In the vertical direction, there is no motion. The sum of all forces is 0. However, if we now sum all the forces in x direction, my force is still 40 newtons from here. And the friction is now negative 30 newtons. So my net force, right, by Newton's second law, is going to be ma, but at the same time it's going to be 40 plus negative 30. Therefore, my ma is now 10 newtons, or mass is 5, so my acceleration is going to be 10 divided by 5 equals to 2 meters per second squared. So you can see that once the body starts moving, because the friction changes, the same force to just start it moving will be enough to keep it moving with the acceleration. Right? If you don't want it to accelerate after it's moved, you need to reduce the applied force, in our case, by 10 newtons. Any questions at this point? Thank you.